Hello and welcome back to Calculus 2, section 6.10, hyperbolic functions. So let's see what hyperbolic functions are. This lecture is going to have a non-calculus part, which is learning about the functions and then algebraic properties and all of that stuff, like for any other function. And then calculus part, which is how to find derivatives and integrals. I just hope that you will not be confusing this with trigonometric functions, because this has nothing to do with trigonometric functions. These functions are borrowing the name in part from trig functions because of the properties, but these functions are not periodic like trig functions are, and they don't behave the same. Now, some of the properties are very similar, so it gets to be a little bit confusing here and there, I understand, but nothing that few hours staring at it won't fix. So where's the idea for something like this? Right? Where does the idea come from? Well, I'm going to write something that we are not going to use in this class at all, which is that sine x can be written as e to the ix minus e to the minus ix over 2I. So there's this complex form through exponentials that can be used to write sine x. And there's also one for cosine. Cosine x is equal to e to the ix plus e to the negative ix over 2. No I in this case on the denominator. So, 300 years ago, 200 years ago, one of the gods of mathematics, Leonhard Euler, figured out pretty much everything we know. And he said, what would happen if he figured out this, and then everything else in terms of the complex, right? What would happen if I am to remove i's, right? So he writes this. He says e to the x minus e to the minus x over 2.
349, the one we...
The first one?
Yeah.
It's empty?
Yeah.
Awesome. So we'll look into that. And then the other one, e to the x plus e to the negative x over 2. And then he worked out all possible, combinations and things, checking what you can do with this thing. And it worked out that most of the things properties kind of remind a lot of properties that we have for basic trig functions. And he said, well, cosine hyperbolic, sine hyperbolic, and so on. So this was hyperbolic sine and hyperbolic cosine of x. So now we know that when you add the exponential function to the decay, right, function divided by 2, we call that sine hyperbolic x. You will need this a lot in your differential equations. So it's not going to be one section and you're done in life. I also plugged in, I think, one of the questions on your lab, number 6, number 7, or whatever is the last question on the first page, should have I hope, cosine hyperbolic. Does it? Yes? All right, great. So you'll have some exposure to it. All right, so now, any electrical engineers around? No? Yes? When you stretch a power cable between two power towers, You do that? This function here is cosine hyperbolic of some sort. It looks like a parabola, but it's not. Anytime you stretch a chord, right, let a chord hang, it forms cosine hyperbolic. For electrical engineering, high power, this is very important because you have to know, right, this in conjunction with Calculus 1, because we know that during the winter it's cold, right, and because it's cold, the cable is going to do what? Shrink. And if there was not enough give, right, it would actually crack, break, snap, whatever you want to use. So it's very important to understand how these functions work and so on. Lots of applications, obviously, in engineering. Otherwise, we wouldn't be learning about these. There are other explanations using the unit circle. You guys can, sorry, unit circle is for trig, hyperbolas. And you guys can, you know, look into that. But I'm going to point out a few definitions. So you saw definitions, and these are the two that you know, must know at all time. So if someone shakes you out of bed, 4:30 in the morning and asks you to define sine hyperbolic, you just go e to the x minus e to the minus x over 2. Right? Or if you're righty. And then you go back to sleep. Now we have the other ones, as the tangent hyperbolic x is going to be sine hyperbolic x over cosine hyperbolic x, which the denominators 2 will cancel off, and you will get e to the x minus e to the minus x over e to the x plus e to the minus x. And cotangent hyperbolic x is going to be cosine hyperbolic x over sine hyperbolic x, which is going to be e to the x plus e to the minus x over e to the x minus e to the minus x. There you go. Yeah, I said it. What happened? Yeah, well, you know them. You know these already. Tangent is sine over cosine. Now hyperbolic tangent is sine hyperbolic over cosine hyperbolic. And these formulas here are just as soon as you divide these guys, the 2's will cancel off. And we have secant and cosecant hyperbolic, right? Right. Secant hyperbolic x is 1 over cosine hyperbolic x, which is 2 over e to the x plus e to the minus x. And cosecant hyperbolic x is 1 over sine hyperbolic x, which is 2 over e to the x minus e to the minus x. Done. Remember how it took a month for all the trig identities in your pre-calc 2? Yeah. Now it's going to take 5 minutes for all of the hyperbolic identities. We're going to have like 5,000 of those. And the kind of, should I say, scary part is that they're so close, but they kind of swap spots. You'll see how they work out. So hyperbolic identities are given on page 493 in our book. And here they are. So cosine hyperbolic x, squared hyperbolic, right, minus sine hyperbolic squared x is equal to 1.
That's 6 and 4.
Page 493. Now, 1 minus tangent hyperbolic squared is equal to secant hyperbolic squared x. And then the cotangent hyperbolic squared minus 1 is cosecant hyperbolic squared x. Oops, x. Dang, I missed this x. What else do we have? Cosine hyperbolic x plus y is actually very close to what we have in the other one. Cosine hyperbolic x cosine hyperbolic y plus sine hyperbolic x sine hyperbolic y, and then sine hyperbolic x plus y is sine hyperbolic x cosine hyperbolic y plus sine hyperbolic y cosine hyperbolic x. And then what else did I? Cosine hyperbolic. So the double angles now. Cosine hyperbolic of 2x is cosine hyperbolic squared x plus sine hyperbolic squared x, and sine hyperbolic 2x is 2 sine hyperbolic x cosine hyperbolic x, and the power reducing cosine squared is cosine, well, 1 plus, I'm going to write it the same way, cosine hyperbolic 2x over 2, actually no, I'm going to put it at cosine hyperbolic 2x plus 1 and sine reduction formula, hyperbolic, erase, cosine hyperbolic 2x minus 1 over 2. So now you're looking at these identities and you might be dreading that they are so close to your trig, but they're actually not the same. Yes?
Should there be a plus somewhere for the sine each dx? No.
Here? No. That's the actually only formula that is identical to trig. Everything else has a slight modification somewhere. I'm going to write a few of these formulas from trig so we can actually compare them on the board. We know that sine squared x plus cosine squared x is 1, right? And if you divide through by cosine, you get tangent squared x plus 1 is equal to secant squared x. And if you divide through by sine, you get 1 plus cotangent squared x is equal to cosecant squared x. So now when you compare these formulas to these formulas, you see that that's pretty damn close, right? If you look at it. Pretty damn close. You have those minus signs over there. All of these have plus signs, and all of these have minus signs. But then, if you remember the cosine 2x formula, cosine 2x formula was cosine squared x minus sine squared x. And now look what you have here, sine squared plus cosine, that's this one, right? So they kind of swap spots, if you think about it a little bit. So you really got to sit down and kind of mull through these so you don't get them confused. All of you should know these formulas here without any doubt now, especially if you're sitting in Calc 2 class. Now that you're looking at the new ones, right, they are very close. What are the other differences? So these two formulas here are identical to the trig. Sorry. Yeah. No, this one. So they are identical to their trig realm. But this one, in a trig, it changes the sign. So for trig, there's a minus there. But for these guys, it's plus. Reduction formulas, these terms are swapped. So it's 1 plus cosine and 1 minus cosine 2x. So they're very, very close. And I hope you guys see why the naming for these functions is utilizing trig. But these are not trigonometric functions. And they do not behave the same as trigonometric functions. So I want to look at hyperbolic function graphs. And I think that this should be. So here I'm going to switch now to PC and look at them. So these are the actual graphs for all of these functions. Are they periodic? Hell no. Every single trig function is periodic from negative infinity to positive infinity. Sine and cosine both infinite waves, and then tangent does its own thing. These guys are not periodic at all. Sure, they have infinite domains from negative infinity to positive infinity like all trig functions do, but they're not periodic. They do not repeat themselves ever. They do what they need to do once, and that's it. So we cannot think about these functions in terms of trig functions at all. The other side of the coin is that the identities that involve two are extremely close, and you saw how close those are. So what are these? Well, these are addition and subtraction of exponential functions that have no complex I, so it's that I that brings in periodicity. If you remember the parallel between, you can go I squared, I cubed, I to the fourth, and then I to the fifth is the same as I, and then I to the sixth is the same as I squared, and so on. It's a loop of 4. Well, remember that your derivative on sine and cosine loops in 4. Sine, cosine, negative cosine, sine, right? Loop of 4. Why? Because i's, right? In a definition. I showed you that the sine is defined through e to the ix minus e to the minus ix over 2I. Those i's actually bring this for loop periodicity in terms of the derivatives. So we have to really disconnect hyperbolic functions from trig because they are not the same creatures. However, their exponential form, kind of close, so that's what these identities kind of work. So what are you expecting on the exam? Well, on the exam, you will be expecting me giving you one of these to prove as an identity. And now how do you do it? You plug in e's and you just grind through algebra. So let's pick one of these. Pick one of these and I will show what I mean. So give me 1, 2, 3, 4, 5, 6, 7, 8, 9. First come, first serve. This one? 8.
Oh, wait, no, 1. No, 8. Yes, 8.
Okay.
8. Now, all others will be done exactly the same way. You will plug in what the sine and cosine hyperbolic are in terms of ease, and you will just grind through the algebra. There's nothing special there. So, identities. So say, prove cosine hyperbolic squared x is equal to cosine hyperbolic 2x plus 1 divided by 2. All right. So how do I do this? Well, on the left-hand side, I will write e to the x plus e to the negative x over 2, everything squared. Because cosine hyperbolic squared, right, you take that square away, replace everything by what you can, and you will get that square there. Equals 2, and now you have on the other side over 2, right? So that stays where it is. You have e to the 2x plus e to the minus 2x over 2, and then you have plus 1. Now observe that the argument of the cosine hyperbolic was 2x, and now the exponents on e's are 2x. So technically here I'll write it on the board. Cosine hyperbolic of a heart is equal to e to the heart plus e to the negative heart over 2. There we go. I usually use flower, but the Singles Awareness Day is coming up, so I'm just gonna use the heart.
Why is all of that over 2?
Yeah, why is it? Because
Yeah, no,
And now I'll put the question mark here. So this is technically, left side, right side, and I'm just going to massage both of them until we get to the same expression on the left and the right. All right. Well, thou shalt square on the left, right? What do I get? E to the 2x plus 2 plus e to the minus 2x over 4. Is anyone screaming, what? Yeah, the middle term, 2ab, when you square something, right? It's going to be 2e to the x times e to the minus x. How much is e to the x times e to the minus x? It's e to the 0, right? Because x minus x is 0. So e to the 0 is 1, 2 times 1 is 2. So there we go. Just a tag of algebra, casual Tuesday thing. On the other side, I'm going to multiply by 2 to cancel the denominator over here. On the first one, I get e to the 2x plus e to the minus 2x plus 1 times 2 is 2 over 4. They're the same. Boom, done. It's literally 2 steps. So just a tag of algebra. Fair? Yes.
if you multiply by 2,
When I multiply by 2, I have 2 terms. On the first term, 2 cancels 2, so I just get these 2 guys. On the second one, 1 times 2 is 2.
yeah, but
On the bottom, 2 times 2 is 4. I multiply 2 over 2, which is 1.
you have
Yeah, we just multiply by 2. All right, good. Guys, I mean, what are you going to do tomorrow? Just prove all of these. Just like the trickiest ones are these two. They're the trickiest ones because they look a little bit different. Have to worry about, because this is going to be e to the x plus y plus e to the minus, in parentheses, x plus y over 2, and you have to massage that. But it's not it's not impossible. So those might be the toughest one.
Can we do one?
Yeah, I just said you should do it.
Why can't we do, like, can you show us?
Oh, you want me to do? What a sneaky way to ask. Can we do one? I said, yeah, go ahead. I mean, I'll call you a bluff anytime. It's like, if you need any help, don't hesitate to ask. You know what I do? I immediately ask. It's like, don't be offering help if you don't mean it. It's like, anything you need. I want Tesla. I want white one. And none of that wooden finishes in. It's not a furniture. Yeah, for a china cabinet to put the coffee mugs and stuff inside, not for a car. It's the greatest piece of technology that exists on Earth right now. Yeah, Model. Model 3 is going to be better?
I think so. Not better, but better in different ways.
Oh, better in different ways. All right, we're going to pause the class because we have to discuss Model S and Model 3. We will, oh, thank you. Now I feel better. You can't tell if I coughed or sneezed.
Right. No,
I know, it's mystery to us all.
just like in general. Terrible.
There's people like you.
What's wrong with people like him? Let's hear it. Cosine hyperbolic of x. Well, look at that smile now. It's like, oh my God, he's going to actually do this. Yeah, I got an hour and a half to kill, so why not? Yeah.
You wrote x, cosine x.
What happened? What's the problem? There's not. Okay, good. Okay. So the left-hand side is going to be e to the x plus y plus e to the negative, in parentheses, x plus y over 2. And on the right-hand side, we're going to have a heart attack. E to the x plus e to the minus x over 2 times e to the x, no, e to the y plus e to the minus y over 2 plus e to the x minus e to the minus x over 2 times e to the y minus e to the minus y over 2. Perfect. Is the string going? Yeah, okay, good. All right. So all we need to do is some multiplication, foiling, canceling, and we're done. There's nothing we can do on the left-hand side. We just leave it and work on the right side. Foil. So it's going to be e to the x plus y. Well, everything over 4 first, right? 2 times 2. It's easy. And then we have plus e to the x minus y and then plus e to the minus x plus y, and finally plus e to the minus x minus y. Plus, and we have one more like this coming up, which is e to the x plus y minus e to the x minus y minus e to the minus x plus y, and I have no room for this one more term, which is plus e to the minus x minus y. It's right there. It fits right there. I mean, I could generate, a lot of paper, which you can do in your notebooks, but then when I export and print, it will not fit nicely in. So I don't want to do that.
Wait, why is that last term plus?
Because here, a negative here and a negative here. Bueno? Now, we have the same terms. Look, e, well, actually, look. We have this term and this term. They're both same terms. One is positive, one is negative. They're both over 4. So they cancel. So these terms die. And in blue, these terms die. What's left? The first and the second term create 2e to the x plus y plus 2e to the minus, and then I'll factor out minus over 4, which is exactly what we need. And if you don't think this is cool, you have no emotion. So awesome. Why, disappointed? Good. Oh, for the moment, I thought you were going to go. Oh. But you didn't. Great. Oh, I just realized something. One thing that you can do on the board, you can't do this while someone is trying to write it, because once you write it on the board, you can just be in the way. Has a lag. That's what happens when we give tablet controls. Time for some calculus. They did not address limits, because why would they, right? You know that you can always deal with the limit. It's just a fancy way to find the y variable and so on. But I would like to discuss that just briefly, because you might run into this in differential equations, and then, it's going to be trouble. In differential equations, the solution is the function. You are used to having an equation and you calculate the answer is 7 and you move along. Well, when you calculate the answer to a differential equation, it's going to be a function. And that function could be sine blah, blah, blah. Now, what we do in differential equations is we take the answer and we shoot it to infinity to check various stuff. So what do we know about a limit of sine goes to infinity? Well, we know it does not exist, because sine oscillates. So when it gets at infinity with the air quotation marks, did it hit 1? Did it hit 0? Did it hit -1? What did it hit, right? Well, that never happens, but yeah. So limit, obviously, for trig function, sine, cosine, tangent, any of them, it's not defined at all. So we don't talk about limits of those vanilla versions of a function in terms of trig. You can figure out what is the, limit of sine x over x at 0 and stuff like that. But now, if I jump to the hyperbolic functions, and now we are staring at all of the hyperbolic functions, which is, I just pulled on a Google, right, hyperbolic function graphs and gave me this, all 6 of them. Look, as the sine of hyperbolic x goes to infinity, the y goes to infinity. For cosine hyperbolic also goes to infinity. This one levels off at 1, right? This one levels at 1. This one goes to 0, and this one goes to 0. So you actually see that now limit of x goes to infinity actually gives, in most cases, gives a number, right? In the previous one, it was not infinity or negative infinity or nothing concrete. It was just does not exist because it oscillates. In this case, again, no periodic behavior. Because there's no periodic behavior, the limit is going to fall somewhere. Whether it's positive infinity, we say end behavior, right? So it's there. So that's the part for limits. Now we jump to the rest of calculus. So you will say, ta-da! What's the derivative of sine? Cosine. What's the derivative of sine hyperbolic? Cosine hyperbolic. What's the derivative of cosine? Negative sine. What's the derivative of hyperbolic cosine? Positive sine. Good. So it's just going to keep you on your toes just a little bit, So just a few of the sine, negative signs are relocated. But other than that, it's identical. It's identical pairing where in trig you have sine cosine pair, secant tangent pair, and cosecant cotangent pair. Same pairing is kept here. Sines with cosines, tangents with secants, cotangents with cosecants. No differences. What else do you know? Sine goes into cosine, cosine goes into sine, tangent to secant squared, right? Cotangent to cosecant squared. So all of that stuff is preserved. The only one thing you have to memorize is that these minus signs that you are used to are just relocated now. They're all concentrated here. So it used to be plus, minus, plus, plus, minus, minus. Now it's just 3 pluses and then minuses. Integrals, same thing backwards. You know the derivative, you will know the integral. So very few modifications here. So losing the minus sign for the second equation, you are used to that, well, you lost it now. And gaining that minus sign on a 5. That was not there. So that minus is relocated from 2 to 5. That's all. The rest is identical to your trig. And all of the good stuff, the U sub and everything else works. Do we want to see pi's in limits to compute definite integrals? Do we? Hell no, right? Because that will be e to the pi, right? We want to see just, I don't know, zeros and ones because e to the 0 is 1 and e to the 1 is e, right? We want to see that. But we definitely don't want to see, pi over 2 there. Again, it has nothing to do with trig. Cosine hyperbolic of pi over 2 is an awful thing, right? Because it's going to be e to the pi over 2 plus e to the minus pi over 2, and then good luck computing that without a calculator. Where the cosine of pi over 2 is just 0, because it's awesome, right? So again, trig world in one bag, hyperbolics in a completely different bag. Hyperbolics have nothing to do with pi's. They're not comparable. They actually make them much worse because you are dealing with two transcendental numbers, e and pi. All right. So stay away. Right? So we don't want to see any pi's in this setup here. If I had the mic, it would be like, just like leave, but then there's another hour or so class, so I'll stick around. I'm going to actually copy this into the notes, which I need to post, but I just wanted to make that, in fact, that you guys already know all of these formulas, and just make a big deal that the minus sign that used to be popping up here, or here, or whatever the hell it was, it's now there. That's it. How do you prove this? Exactly. Just write it in terms of ease, and then just how easy or how hard is to differentiate that? Not hard at all, right? And maybe that's going to be a good exercise for you to see where you lose that minus sign. Like, don't you go, but why? Why do I lose my minus sign? Well, what's the derivative of e to the minus x? Yeah, it's a minus, right? So that minus from the exponent traveled down. And then there was a minus from the sign. Minus and minus gives a plus. And then there's nothing to factor out. So by the end of this class, when you do power series, you guys will know a lot about trig and derivatives of trig and stuff, and why things work the way they work. For now, we don't know kind of those things. We memorized a bunch of stuff. So now, these will just adjust minus signs a little bit, and then the life is going to be beautiful again. What kind of questions? Area under the curve. You set up the integral rate of change. You set up the rate of change. You will set up your derivatives and stuff. So there's nothing special about this in terms of calculations. The only new thing is that all of these identities, whether they're basic identities or calc identities, they can all be proved through writing cosine as e to the x plus e to the minus x over 2, and then massaging that, whether you have to integrate or differentiate or whatever else you need to do. Fair? Well, the break starts now, and well, I still have to write the formulas. And then after the break, there is a lab, and at some point there is a commute back home. At some point, we'll see. So I'm going to write these formulas and then stop the stream. So the derivative of cosine hyperbolic x is sine hyperbolic x, which means that the integral of sine hyperbolic x dx is cosine hyperbolic x plus c. Five to go.
Isn't there an option to like copy and paste like images into the thing?
Oh yes.
So, yeah, you could just do that.
But
It's not the same.
no, it is the same, and it's much faster than this. But it gives me joy to write it. It's the same reason why I like headaches.
Makes you feel alive.
No. It makes you, when you have a headache once in a while, it just makes you appreciate more all the days when you don't have one. Which is completely different than someone who has migraine and a headache every day. That would be a problem.
Yeah.
But, in my case, like 2-3 times a year, welcome it. And now the minus ones. And that's it. No grand finale or anything like that. You just buy.